our today in our little puzzle. And today we're going to look at using those. Okay. So, just for kind of some context, if I had something right, what would I want to do with that? Simplify it, right? So like I would add my 2x and my 5x, I'd want to distribute my 2, and then combine my like terms. Yes? Because then like if that's an equation or I'm trying to graph that, right? If I have something that's in simplified form, it's much easier to deal with. Okay? Which is also helpful with our trig expressions. The only difference here is that because my trig expressions I have sines and cosines and tangents and all the things, none of those are what we can call like terms. So like you can't just add them or subtract them, right? So in order to simplify them, we have to use our trig identities instead. But our goal is still the same. We're still trying to start with something that is longer or has lots of operations, and make it into something that's smaller with fewer operations. There we go, so that's kind of our purpose. And in order to simplify our trig expressions, we have to use our trig identities, which is why we wrote those out first. So we're looking for two main things whenever we're simplifying a trig expression, okay? The first is that we want the least amount of trig functions. And then we also want the least amount of operations. Because again, we're trying to start with something that's a little bit bigger and make it into something that is smaller or not as complicated. Alright, so on your last little flip of your foldable, it should say strategies, okay? We're going to have like 4 or 5 of these, so just be careful, like don't write super big on them. But our first strategy that we're going to look at is to convert to sines and cosines. So you might remember it. Convert to sines and cosines. And the reason that we like to do that is because sines and cosines are in a lot of our different identities. And so a lot of times we can convert all of the stuff to sines and cosines, and sometimes we can end up simplifying stuff out. So like on this first one, notice that I already have a sine, and so if I already have a sine or cosine, that's usually a good indication that maybe I want to convert the other stuff to sines and cosines. So right now we have 2 trig functions and 1 operation, so we're trying to reduce that. Okay. So is there a way that we can rewrite cotangent using sines and cosines? Bless you. Thank you. So yeah, cotangent is equal to cosine over sine. Which of our identities is that? Quotient. So you don't have to label them. I'm going to label them just so if we refer back to them later, we know what we did at each step. So it's not a bad idea to kind of put which identity you use, but you don't have to. Then what do we notice?
A sign on the bottom.
Okay. Anything else?
The cross has a sign on top.
Yeah, so now we have sign on top and bottom. So then what are we left with?
Cosine.
Just cosine. So do I have less trig functions than what I started with? Yeah, and then do I have less operations? Yeah, I started with multiplication and now I don't have any. What do we notice about our second one? Yeah, so we notice that we have a squared, which all of our Pythagorean are squared as well. So that's one of our second strategies, is to look for squared terms. And the reason for that one is because a lot of times when we have squared terms, that means that we're going to apply one of our Pythagorean identities. So you might want to write that strategy in the last box. So look for squared terms. So we have three Pythagorean identities. Remember, our first one is sine squared plus cosine squared equals 1. So we have a sine squared out here, but notice that I don't have a 1 and I don't have a cosine squared with it. We got okay with that? So there's not a whole lot I can do with that one. However, on the inside one, I do have a 1 and a cotangent. So which one of our Pythagorean identities has a 1 and a cotangent? Yeah. So remember the second one that we looked at yesterday was 1 plus cotangent squared equals cosecant squared. Okay? And remember that our identities are equivalent, meaning that if I have 1 plus cotangent squared, I'm allowed to substitute cosecant squared for that. So now this becomes cosecant squared up there. So we have less operations now because I started with multiplication and addition. Now I just have multiplication. However, I still have two trig functions. So sometimes we might have to use more than one identity. Okay, so we started by looking at that I had squares, so we used our Pythagorean. But then also notice that we're in kind of a similar boat that we were with our first one. I have sine, and then I'm multiplying it by something else. So let's also think about, is there a way that we could rewrite cosecants with sines or cosines?
1 over sine.
Which is our reciprocal. And because it's squared, it will be 1 over sine squared. But yes, it's our reciprocal. So now what happens?
The sines cancel out.
They reduce, but yes. And what are we left with? That's pretty, I think that's as simple as it gets, right? So the way that I like to think about these is that they're kind of like puzzles. Like you're trying to figure out like which identity you have to put where in order to piece together to kind of make it like work out. So they're kind of fun in that way. I will say that they are hard in the sense of like there's not a formula or like a rule that we follow every single time. Which is why the little box at the end says strategies, because we have some different things that we can try, but there's not necessarily like one right way to solve each of these, okay? Which also means that it's going to be important that you do your practice on these, because the more that you practice with using your identities, the better that you get at like noticing those small things of like which one to use when. Questions on either one of those? Okay. Then look at another one. So I have sine of x times cosine squared of x minus sine of x. So notice that we have two major operations. So I have multiplication and subtraction. And we also have 3 trig functions, right? I have 2 sines and I have a cosine. Agreed? Okay. Now, be careful, because a lot of people's first instinct is they see the 2 sines, they see subtraction, and what do they want to do? Just combine them and make them go away, right? But be careful, because technically this would be like if I had an x, y squared minus x, right? These are not like terms, because they do not have the exact same thing. Which again is the whole reason why we have to use our trig identities, like I said, is because most of the time we can't just combine things by adding and subtracting. Okay? But what might we do instead? I can't really convert 2 sines and cosines because I already have sines and cosines. Yes? Other idea?
You divide by sign.
So, no. Well, you're on the right track. So no, I can't just divide by a sign because, think about like if I just had 4, right? My goal is to keep writing equal sign. So if I just divide by 2, can I put that equal sign there? Like if I actually had to say 4 equals 2. No, so the same thing, if I just divide by sign, right, then I can't put an equal sign because I'm dividing by something which changes the value of it. Are we going to do that? Which is different than like if I have an equation, then I could because I can do it to both sides. Okay? However, is there something that we can do that's kind of like division, but doesn't like completely get rid of the number? Just like moves it. So we're still gonna take that out of both of them.
Factoring out the sign.
Yeah, I can factor out the sign, which we are allowed to do because I didn't technically get rid of it. I'm just moving it to the front. Are we all with me there? So, right idea, we just have to do it a little bit more strategically so that we don't change what it actually equals. So, if I factor out a sign, which is kind of like dividing, what are we left with on this first term?
Cosine squared.
Just a cosine squared. And then what are we left with on that last term? Minus 1. Okay. So we're getting better, right? So instead of 3 trig functions, now I only have 2. Okay, but we still have quite a few operations, right? I still have multiplication and subtraction. Do we notice anything else? So we already said I can't convert to sines and cosines, so they already got that. What was our second thing that we wanted to look for?
Look for square terms.
Huh?
Look for square terms.
Squared terms. Do I have a squared term?
Mm-hmm.
Yeah, which one?
Cosine.
Cosine. And that also happens to be next to a
1.
1 now, yes? So which one of our Pythagorean identities has a cosine squared and a 1 in it?
Squared plus cosine squared.
Yes? Now, remember, our identities are equations. Yes? So I am allowed to add, subtract, multiply, and divide things to both sides of this, because this is an equivalent statement. Alright, y'all with me there? Because I want one side of this equation to look like that. The thing that I have on the inside. Yes? So what might my first step be?
Subtract sign.
Go in. Okay, so now I have my cosine by itself. Then what?
Subtract 1.
So I have cosine squared of theta minus 1 equals negative sine squared of theta. So does one of my sides match what I have on the inside? Yeah, so that means that if this side matches this, okay, and these are equal, okay, what am I allowed to do then with that other side? a negative sine squared instead of not theta but x my other. And now we can kind of think, we can combine these, because if I'm multiplying two things, so think about it, if I had like x times x squared, what do I get? X cubed, which is the same thing here. If I have sine times sine squared, I'm going to get a sine to the third. And remember for our trig functions, we write, just like I have in the squared, we write that exponent like in between our sine and our x, and the reason for that is because like if you write the 3 out here, it can be confusing on if you mean that it's supposed to be with the whole thing, and if it is with the whole thing, you need to put parentheses. If it's not with the whole thing, it's just with the x, then you don't have to put parentheses. But just to save from having to put the parentheses there, that's why we write it in the middle instead. If you didn't know. So now that's pretty simplified, right? Now I only have one trig function, even though we still have two operations technically because it's negative and it's cubed, okay? I still have reduced the number of trig functions that I have, which is still much nicer. Which questions do you have? Maybe. Alright, so this time on the first one, okay, what do we notice is different about it than the other ones that we dealt with? It has a negative angle, right? The negative's on the inside. Okay, we had some that had negatives, like the negative sign. Those were all on the outside. Okay, so let's think or look at which one of our identities have negatives on the inside. The even and odd, and tangent is a odd. So what does tangent of negative theta equal? Negative tangent of theta. Okay. So that goes for both of these. So the next kind of strategy is to look on the inside. Meaning like look on the inside of our angles. So like do I have negatives there, and then on this next one I have a plus 90, which is a different thing. But so look on the inside of our trig function. So we're starting to look a little bit better. I don't have a negative on the inside, that's good. But I still have two trig functions. Are either one of them squared? No. So I can't use the Pythagorean. But we can go back to, can I convert everything to sines and cosines? Yeah, what can I rewrite tangent as? So sine over cosine. And what can I rewrite cosecant as? So then what happens?
The signs reduce.
Agreed. And what are we left with?
1 over cosine.
Negative, but yes. And that's still not bad because I have just one trig function, but I still have an operation there. Is there a way that we could rewrite 1 over cosine? Yeah, we can rewrite it as secant of theta. And that's nice because now we just don't have to deal with a fraction, which is helpful. No, maybe? What questions do we have on that one? Alright, looking at the next one, what does that, if I look at the inside, what does that look similar to?
Your co-functions.
Okay, is it my co-function though?
No.
No, what's wrong with it right now?
It's adding and subtracting.
Oh, okay. What could I do? Well, if I need it to be subtracting, right, which one is supposed to come first?
Minus.
Okay, and I want to change it to subtraction, but I can't technically change the sign of that. What would that be instead? Minus a negative would make it a positive, yes? Are we okay with that? And so basically we can kind of say, okay, instead of us being able to say that this just equals cosine of theta, right? I have to do whatever's in the parentheses right here. So this equals cosine of negative theta instead. He's basically like, this could be whatever. This could be a smiley face, and then this would be a smiley face, right? As long as I can rewrite it as 90 minus something, then that's going to equal cosine of that something, whatever was on the inside of that parentheses. Are we with me there? Okay. But now, what do we know about cosine of negative theta? Cosine's an even function, so what do we end up with?
Cosine.
Just cosine of theta. Which again is much nicer than what we started with. What questions do we have there?
So, what'd you do to make the multiplier?
I used our co-function identity. So remember that our co-function identity is that sine of 90 degrees minus theta equals cosine of theta. But this time, since I didn't just have a theta there, I had to write whatever I was subtracting, which was technically a negative theta instead. Other questions? Alrighty.